Imagine a tunnel. Not just any tunnel, but one that connects two distant points in space and time. This is the captivating idea behind wormholes, hypothetical shortcuts that could revolutionize our understanding of the cosmos. Wormholes, also known as Einstein-Rosen bridges, emerge from the enigmatic equations of Einstein's general theory of relativity. They are theoretical tunnels that bridge two different points in space-time, potentially allowing for faster-than-light travel and journeys to distant corners of the universe. While the concept might sound like something straight out of science fiction, wormholes have captured the imagination of physicists and astronomers for decades. The possibility of traversing vast cosmic distances in the blink of an eye is an alluring prospect, to say the least. But how much of this is based on scientific theory, and how much is still in the realm of speculation? The answer, as with many things in astrophysics, is complex and full of intriguing possibilities. Join me as we delve into the fascinating world of wormholes, exploring their theoretical underpinnings, the mind-boggling challenges they present, and their enduring presence in popular culture. Let's embark on a journey to unravel the mysteries of these cosmic shortcuts and explore the tantalizing question: could wormholes be the key to unlocking the universe's deepest secrets? To grasp the concept of a wormhole, imagine a piece of paper folded in half. This simple analogy helps us visualize a complex idea in a more tangible way. Now picture a tiny ant trying to get from one side of the paper to the other. The ant represents us, trying to navigate the vast distances of space. It could crawl across the surface, which would take a considerable amount of time. This is akin to how we currently travel through space, moving from one point to another over great distances. Or it could burrow a hole directly through the paper, creating a shortcut that significantly reduces its travel distance. This shortcut is what we refer to as a wormhole. This, in essence, is how a wormhole is theorized to work. It provides a direct path between two points, bypassing the conventional route. Instead of traversing the vast distances of space conventionally, a wormhole proposes a shortcut through the fabric of space-time itself. This could revolutionize our understanding of travel and distance. It's like folding the universe so that two distant points are brought closer together, connected by a tunnel-like bridge. This bridge could potentially make interstellar travel feasible within human lifetimes. This bridge, the wormhole, could potentially allow us to travel between these points much faster than traveling through conventional space-time. Imagine being able to reach distant galaxies in a matter of moments. The theoretical basis for wormholes lies in Einstein's general theory of relativity, which describes gravity as a curvature of space-time caused by mass and energy. This theory has been fundamental in shaping our understanding of the universe. Just as a bowling ball creates a dip in a stretched rubber sheet, massive objects warp the fabric of space-time around them. This warping is what we perceive as gravity. Wormholes are predicted to be extreme distortions of this curvature, creating tunnels that connect different regions of space-time. These tunnels could theoretically link distant parts of the universe. However, while Einstein's equations allow for the existence of wormholes, they don't tell us how to create them, or if they are stable enough to traverse. This remains one of the biggest challenges in theoretical physics. This is where the distinction between different types of wormholes and the challenges associated with them comes into play. Some wormholes might be traversable, while others could be purely theoretical constructs. The quest to understand and possibly harness wormholes continues to drive scientific inquiry and imagination. The most exciting type of wormhole, at least from a science fiction perspective, is the traversable wormhole. These hypothetical passages through space-time have captured the imagination of writers, filmmakers, and scientists alike. Imagine stepping through a portal and instantly finding yourself on a distant planet, light years away from Earth. The concept is both thrilling and mind-boggling, offering a glimpse into a universe where the vast distances between stars and galaxies could be bridged in the blink of an eye. This is the tantalizing promise of a traversable wormhole, a cosmic shortcut that could allow for rapid transit across unimaginable distances. Such a phenomenon would revolutionize space travel, making interstellar journeys feasible within human lifetimes. However, the reality of traversable wormholes is far more complicated than their fictional counterparts. Theoretical physics presents numerous challenges that must be addressed before such a concept could become a reality. For a wormhole to be traversable, it needs to meet some stringent requirements. These requirements are not just theoretical hurdles, but are deeply rooted in the fundamental laws of physics. First and foremost, it needs to be stable enough to allow an object to pass through without collapsing. Stability is crucial because an unstable wormhole would close up before anything could traverse it, rendering it useless for travel. This is where things get tricky. The equations derived from Einstein's theory of general relativity suggest that wormholes, if they exist, are inherently unstable. Einstein's equation suggests that wormholes, if they exist, are inherently unstable and prone to collapsing faster than the speed of light. This rapid collapse would make it impossible for anything to pass through safely. This instability means that a naturally occurring, traversable wormhole is highly improbable. The forces at play would cause the wormhole to pinch off and close almost instantaneously. However, some physicists have theorized that it might be possible to stabilize a wormhole artificially using something called exotic matter. This exotic matter could provide the necessary conditions to keep a wormhole open. Exotic matter, unlike the ordinary matter we are familiar with, possesses negative mass and negative energy density. These unusual properties could counteract the natural tendency of a wormhole to collapse. While we have never directly observed exotic matter, its existence is theoretically possible within the framework of quantum physics. Quantum theories allow for the existence of particles and states of matter that defy our everyday experiences. If we could harness exotic matter, it might be possible to prop open a wormhole, preventing it from collapsing and potentially making it traversable. This would be a monumental breakthrough in our understanding of the universe. However, even if we could stabilize a wormhole, there are still significant challenges to overcome. The practicalities of creating, maintaining, and navigating such a structure are daunting. These challenges involve some of the most fundamental laws of physics, such as causality and the conservation of energy, and they lead us to question whether traversing a wormhole is truly possible. The implications of breaking these laws could have profound effects on our understanding of reality itself. The debate continues among physicists and cosmologists, with some optimistic about future discoveries and others skeptical of the feasibility. As our understanding of the universe deepens, so too does our appreciation for the complexities involved in making science fiction a reality. Whether fact or fiction, the concept of traversable wormholes remains one of the most fascinating and enigmatic ideas in modern science. It challenges our perceptions of space, time, and the very nature of the cosmos. As we continue to explore the mysteries of the universe, who knows what incredible discoveries await us just beyond the horizon. The first type of wormhole ever theorized, the Einstein-Rosen bridge, presents a different set of challenges. These theoretical constructs, named after the famous physicists Albert Einstein and Nathan Rosen, have intrigued scientists and science fiction enthusiasts alike for decades. These wormholes, named after their discoverers, are essentially tunnels connecting two different black holes. Imagine a tunnel that could, in theory, link two distant points in space, creating a shortcut through the vast expanse of the cosmos. While they are theoretically possible within the framework of general relativity, they are not considered traversable in the traditional sense. The equations suggest that such bridges could exist, but the practicalities of traveling through them are fraught with insurmountable challenges. The problem with Einstein-Rosen bridges lies in their inherent instability and the properties of black holes. These structures are incredibly unstable, and any attempt to pass through them would likely result in their collapse. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape its pull once it crosses the event horizon. This immense gravitational force is what makes black holes such fascinating yet dangerous objects in the universe. This means that even if you could enter an Einstein-Rosen bridge through one black hole, you would be trapped inside, unable to escape the gravitational pull of the other black hole at the other end. The journey would be a one-way trip with no possibility of return. Furthermore, the singularity at the center of a black hole, where all matter is thought to be crushed into an infinitely small point, poses a significant obstacle. The singularity represents a point of infinite density and zero volume, where the laws of physics as we know them break down. It is highly unlikely that any object, let alone a human being, could survive the journey through a black hole singularity. The intense gravitational forces would stretch and compress any matter to the point of destruction, a process known as spaghettification. So, while Einstein-Rosen bridges are fascinating theoretical objects that deepen our understanding of black holes and the fabric of spacetime, They don't offer the same potential for interstellar travel as traversable wormholes. They serve as a reminder of the extreme and often hostile conditions that exist in the universe. They remain a one-way ticket to the unknown, a testament to the extreme conditions that exist within our universe. The study of these bridges continues to push the boundaries of our knowledge, challenging our understanding of space, time, and the very nature of reality itself.
Like and subscribe to start your journey today.